Now let's talking about the ensemble estimators. So today we will be dealing with bagging estimators and boosting estimators. For both bagging and boosting, they are built based on the combined effort of a large number of weak learners, or in other words, base learners. So for bagging estimators case, we are training those weak learners simultaneously. And for boosting case, we are training those weak learners sequentially. Now, let me explain in more details, utilizing specific classifiers. So for the bagging estimators, today we are dealing with a random forest algorithm. For random forest algorithm, our base learner is just decision tree. So here, let's just import that random forest classifier. So we are from the Ensemble module, importing the random forest classifier. Then as for the instantiating, we use RNF, and we are instantiating utilizing the random forest classifier we just imported from the Ensemble module. And we are inputting the hyperparameter as maximum of the depths, max depths, being equal to 5. So the optimum depths we just found out. And then we are just doing training as usual. We are fitting on the training set. And then we are making out of sample predictions, again, using the predict method and based on the test set, like for the features. So X test, and we are assigning the out of sample predictions to the variable called as Y test spread. Then we are measuring the out of sample accuracy. So we are measuring that out of sample accuracy using accuracy score from the matrix module of skNear. So for the first input of that function, that's going to be the label on the test set. And we are inputting the actual labels. That is Y test. And also the second input is the predicted labels. That's our out of sample predictions, Y test spread. Then we also print out our out of sample accuracy score. Also, aside from this out of sample accuracy, we also want to have a look at the out of sample investment performance. So we are feeding the out of sample prediction and the prices, like again into the ML analysis function from our AP module. I still want to remind you guys that whenever you are using the ML analysis function for the first input, basically for the predictions array, what you want to do is that you want to add index to that array. And of course, you want to convert that into a PD series object and with the indexes. So the index would be the stock ticker and the date. Also, we are having this last line DIA here because we want to display the diagnostic table. So now let's execute this code here. While the code is running, let me explain the intuition for the random forest algorithm again. So for the random forest algorithm, it's built on the basis of decision trees. So in other words, its weak learners are decision trees. And what the random forest algorithm does is that as a bagging algorithm, it's training all those decision tree learners simultaneously. So all at the same time. And then what it does at last is that it will take the average votes of all the trained decision trees as a prediction of the random forest model. So basically the random forest output is going to be the average vote of all the decision trees. So that's the intuition behind it. While the code is running, let's also execute the next cell. So the next cell, as already shown here, it's the feature importance of this random forest classifier. So here, let's also execute that. But as we have already seen from the result here, we are assigning higher importance to the low volatility factor now than the original decision tree model. So for the decision tree model, the feature importance of this low volatility factor is actually very, very close to 0. So essentially just 0 for the decision tree model, meaning that for the decision tree, when we are splitting in terms of the different nodes, actually the low volatility factor doesn't play a role in terms of splitting of those nodes. But it's not the case for this random forest classifier. Let's also take a look at the out of sample accuracy here. That's 0.524. Let me check what's the out of sample accuracy for the decision tree. I think for the out of sample accuracy for the decision tree, that's actually even higher than the random forest classifier. So we don't have any improvement in the performance comparing to the decision tree model. But let's still try other ensemble methods to see if we are able to improve the performance. Now on to gradient boosting and also the adaptive boosting actually. So those are all boosting algorithms. For gradient boosting, actually let me expand boosting again, then I will introduce gradient boosting and ADA boosting individually. So for boosting algorithms themselves, the weak learners, the base learners, are going to be trained sequentially. It's no longer trained simultaneously as in the bagging's case, but instead they are all trained sequentially. For gradient boosting, the gradient boosting is trying to fit not to the original sample data themselves, but you are trying to fit the new predictor to the residual errors from your previous predictor. In this classifier's case, you are trying to fit the new predictor to your realized outcome label. So for example, your model predicts that the probability is 0.8, then the residual error is just going to be 1 minus 0.8. That's going to be 0.2. And your training is done on that data 0.2 in terms of the new predictor. That's gradient boosting. Of course, gradient boosting can be more naturally implemented in the scenario of regression tasks, because for that case, the residual error is simply defined as the difference between your outcome variable minus the predicted value of that outcome variable, right? So for example, what I'm trying to say is just y and y hat. So y and estimated value of y. So that's a residual error for the regression tasks of gradient boosting. But now we are classifying using gradient boosting. Now let's get back to the codes here. So from sklearn.ensemble, I'm importing gradient boosting classifier. And here I'm specifying the maximum depth, max depth, is equal to the optimum depth we just calculated for the decision tree, which is 5. So the base learner here is still the decision tree. And we are fitting this new classifier, gradient boosting classifier, which is instantiated as GBT. We're fitting the GBT to X train and Y train. And as usual, we are measuring out of sample predictions using the test set. We are calculating the out of sample accuracy based on the actual labels and the predicted labels for the test set. Then for the out of sample investment performance, again, we are using ML analysis. And the first input is going to be the out of sample predictions with the added indexes. And also the second input being the prices. And again, we are inputting DIA here at the last row, simply to display the diagnostic table. Now let's execute that. Let's also execute the next cell. While the code is running here, let me explain what is ADA boosting. So for boosting algorithm, as we discussed earlier, boosting is all about training new predictors, like training predictors sequentially. For the gradient boosting, each new predictor will be fitted based on the residual error from the last round, like from the previous predictor. So in other words, we are training our weak learners basically based on the residual errors after the first round. So for all the following rounds after the first round, we are simply doing the training using residual errors. The ADA boosting works differently. So for ADA boosting, we're still training based on the original data sets. We are not training based on the residual errors. So here we are still training the predictors sequentially, but now we are paying more attention to the training instances that we got them wrong. So for example, if I labeled a class 0 as class 1, I'm trying to say if that my model made a mistake and mistakenly labeled that class 0 as class 1, then in the next round, in the training of the next predictor, I'm just going to place more weight on that wrong instance. So that's adaptive boosting. Let's actually still execute the code here. Nothing much new here. So the thing new is that we are importing the ADA boost classifier. So that's a classifier, that's a class predefined for the ADA boost classifier algorithm. And then we are instantiating that classifier. When we are instantiating the ADA boost algorithm, we have to specify the base learner. So now the base learner is not necessarily decision trees. So we can also use other classification algorithms here. But for illustrative purpose, here we just stick to the decision tree with a depth level of 5. That's why we pass this parameter into the class. So we specify that for this model we are creating here, we are still using the decision tree as the base learner. More specifically, the decision tree with the depth level 5. So we're still doing the training. So we're using the fit method. And then based on that trained model, our new classifier here is named as BDT. And we are just fitting BDT to X train and Y train. Then we just use the trained model BDT, and we use the predict method of that classifier of that model. And then we input X test to get the out of sample predictions. We store those values in the Y test spread. And then based on that out of sample predictions, again, we are calculating the out of sample accuracy and also the out of sample investment performance. Let's also execute the code here. So now I'm just waiting for the execution of those 3 cells. Let me also execute for this features importance here. So the final cell of the notebook today here is again just a feature importance. It's a feature importance of the ADA boosting classifier. It's so again we are using the classifier, the trained model BDT, and we are just taking the feature importances property of that trained model. So here we are creating a data frame based on this property here. And for that data frame, we are letting the column names to be feature importance. And we are letting the index to be equal to the column names for our feature data set X. So which are basically just the names here. Our gradient boosting result is out now. And our ADA boosting execution are still running. Now let's take a look at the gradient boosting result. So here, our out of sample accuracy 0.525 still remain quite the same as the decision tree model. For the random forest estimator, as I said earlier, basically it doesn't improve no matter we are comparing the out of sample accuracy or the out of sample investment performance. If we go back to the gradient boosting results, we can see that though the out of sample accuracy remains the same as the decision tree classifier, but we do have some improvement in terms of the investment performance. So you can just compare this table with the same diagnostic table of the decision tree classifier. You will find that we would be having higher active returns here. Let me find. Yep. For example, if you look at the active returns, this is the result for the decision tree. That's going to be 0.077276. Now, if you go to the gradient boosting, you see the active return actually now improved to 0.08-ish. And also now if you look at the feature importance, now we are utilizing a low volatility factor even more. So the feature importance increased compared to the random forest classifier. Now ADA boosting. So let's just wait a bit for the ADA boosting classifier. So now our out of sample accuracy actually improved. I remember that for the decision tree, that out of sample accuracy is actually 0.525, right? But for this ADA boosting here, our out of sample accuracy now increased by 0.001. So now it increases to 0.526. And the active return is also higher. And the active return of the ADA boosting is even higher than the active return of gradient boosting. And also for the feature importances, still we are utilizing this slow volatility factor more when we are using the ADA boost algorithm than when we are using the decision tree algorithm. Now let me do a summarization on the bagging and boosting again. And then I will end the session today. So for bagging and boosting, they are all about training base learners and take the average results, take the average votes of the base learners. Not really the average, but maybe the weighted average vote of all the weak learners to form the prediction of the final model. But for bagging, for the difference between bagging and boosting, the difference between the two lies in the training sequence. So for the bagging estimators, we are training all the base learners simultaneously. While for the boosting, we are training the base estimators, base learners, sequentially. So with a sequence. So for example, we train tree A first, and then train the tree B secondly. So that's a core difference between bagging and boosting. So whether you are training simultaneously, meaning in parallel, or training sequentially. That's pretty much all the content of today. What I want you guys to do is that I might be holding the Q&A sessions in the form of Zoom before your final exam. So I will also make announcement on the time of those Q&A sessions. I will make those announcements on Canvas. So I want you guys to like, if you have any questions, just ask me those questions during the sessions. And also, if you don't feel like attending those Q&A sessions, you can also just message me and asking me about all your questions. Yeah, that's it. It's really a great semester. I really enjoyed the semester with you guys. Bye. Thank you, guys.